Hi there. I wanted to do a video on an active loop antenna I built some years ago. I don't know if you can see this one very easily. It's not really much of a loop at the moment because I had to squash it to get it in the car because it normally lives at my mother's house. And it developed some problems, so I had to bring it home. Because occasionally I stay up at my mother's house. But this one's a 0.9 meter diameter loop, and I've got another one up the garden here which is a 1.2 meter diameter loop, which I've been using for a few years. And the history behind it is a few years ago I used to use a wire aerial. I still do use a wire aerial for mainly listening to the amateur bands, 160 meters, 80 meters, whatever. And I was finding that since I'd moved here, over the years, the noise level was dramatically increasing with all the switch mode power supplies and stuff that people have got in their gardens, in their houses, I mean. All the switch modes, whatever. So what I wanted to do was put up a loop as far away as possible from the sources of interference. Also, it could be very useful to use when you get thunderstorms around, because you don't want to be plugging in a wire aerial to your receiver when you got thunderstorms. So obviously you get really high voltages even if you don't get a direct strike. So with a loop, it's so small, you're not going to have any problems like that. And this one I constructed a few years ago. There are companies making them. There's one in this country, and they're charging about 200 quid for these things. Mine cost me about 35 roughly to make, and whether mine's would perform worse than the ones you can buy, I don't know. But I'm happy enough of how it performs, and it is very directional, so you can null out sources of interference. So next I'll go over the construction and the circuit diagram and design. Okay, this is the circuit diagram of the active loop, and it basically consists of your loop, which is any size you want basically. The bigger the better, ideally, but then you've got mechanical problems with if it gets too big it's going to need more support. But anyway, the circuit is basically a 2 transistor amplifier with a common emitter resistor, and this design, which I got off the internet, which is fairly easy to find if you look up active loops, uses a couple of BC547s, which are fairly low powered TO92 transistors. Now, they won't take a lot of current, so the main problem I noticed when I was running it at low currents, like the original design is for a total current of 75 milliamps split between the 2 transistor, so roughly 37 per transistor. And at that sort of low current levels, I tended to notice I was getting intermodulation distortion from high powered medium wave, long wave transmitters. So I wondered what would happen if I increased the collector current. So I went for a higher power transistor, which is a 2N 3866, which is a TO5 style transistor, and it's got a reasonably high gain into the low VHF frequencies, so it should be ideal for HF whatever. So I then increased the collector currents up to roughly 75 milliamps per transistor, and that seemed to make a fairly dramatic difference to the intermodulation. I tested it on a spectrum analyzer, put two RF generators connected together for a combiner, and did the test about 10 megahertz, spaced the frequencies about 1 kilohertz apart from the two generators, and by doubling the collector currents on the transistors, it dropped the intermodulation products by 10 dB, which is certainly worth doing. The rest of the circuit is fairly simple. The loop is coupled into the base of each transistor for a 0.1 microfarad capacitor. Then you've got your biasing components. The original design had a 50 ohm resistor in the emitters. I've got a 33 ohm now in there, and in the collector the original design had 100 ohms in each collector. I've lowered that to 68 ohms to get the collector current increased, and changed the biasing to increase the collector current. Then it's just the outputs from each transistor is coupled to a bifilar wound transformer, which they specify as a FT3743, but I just used any old toroid I had in my junk box. I think it came out of a switch mode power supply, and it seemed to work fine. So the signal comes out of there and goes down the coax, and also you're feeding DC down your coax from your house, from the receiver obviously. So this bit represents the coax, secondary the transformer, primary transformer, and that's an inductor, 1 millihenry roughly inductor with a resistance of 10 ohms, which feeds power back down the coax, and DC blocking capacitor to the receiver. And with a 10 ohm resistance on the inductor, you're getting roughly 1.5 volt drop through the inductor, which is no problem really, because I'm running on 13.8 volt power supply next to my receiver. So you're still getting 12 volts up at the loop without any real problem. So as you can see, I've redesigned it considerably. I've put heat sinks on the two N3866s, because although they're only dissipating 0.2 watts, if you could imagine it being outside in a hot day, it can often be over 30 degrees here in the summer, and it's fully exposed to the sun. It's going to get pretty bloody hot in the box. So, but I've never had any problems with it overheating and transistors dying. So next I'll do have a look inside the box of the construction. Okay, this is the inside of the box, which is connected to the aluminium loop. There's the two transistors and the emitter resistor. The signal comes in at the side here, where I've got the loop bolted on with 2 4mm bolts which go through the box. That's the problem I had with this. The water was getting through there, through those where those bolts go through. So I've now put a layer of self-amalgamating tape between the aluminium and the box, hoping that'll stop it getting in. The other problem I had, I didn't have any holes in the bottom of the box, so it was just collecting in there and going nowhere. So as I said, it comes in here and it's connected to this coupling capacitor, and that goes into the base of the transistors, and it's the same on the other side. That's the 2 collector resistors, 68 ohms there. Normally you take power in through the coax, so it comes in on the secondary of the transformer, and that goes straight to the positive rail for the circuit. But when I'm testing it here, I've got the wire that normally goes to the center of the coax down to earth, and I'm just feeding in 12 volts to that point. That's the core. As I said, it's roughly 15 turns of bifilar wound enameled wire. I guess the more turns you have, the lower the frequency it will work at. I mean, I've used this between 60 kilohertz. I've picked up the 60 kilohertz MFS signal, timecode signal, no problems on this. So it has got a very good frequency range, and it will work up to at least 30 megahertz. Although I really normally only use it in the 160 meter, 80 meter and 40 meter bands, but occasionally use it for broadcast reception on medium wave, long wave. And as you can see, I've made a printed circuit board up. It's just the easiest way, quite a simple circuit to build. And the socket on the front is SO239. That just came out of a scrap wireless microphone receiver, and it's all built in a waterproof plastic box, which was waterproof until I drilled holes in the side of it. Next, I think I'll show you some signals on the spectrum analyzer. Okay, now we're looking on the spectrum analyzer, the signal coming out of the loop, and I've got it set to one of the strongest stations around here, which is radio 4 on 198 kilohertz in the long wave band. And I've got a reading when I do peak search of about -40 dBm, which is a fairly big signal in radio terms. Now I'm going to try and demonstrate the directivity of the loop. Obviously I don't think it's going to work as well inside the workshop as it would outside, but I'll just get it out the vise and twiddle it around a bit. So right, I'm turned it through about 90 degrees or so, and it's dropping the signal down to -54ish. Actually, you can go lower than that, but yeah, so maybe a drop of about nearly 20 dB, but it's not the ideal place to be testing it. I'll just see what other signals I can see on the spectrum analyzer. I'll put it back in the vise. Right, the spectrum analyzer gets a bit upset sometimes. It's saying there's an ADC overload, It's probably because of all the other signals from stuff I've got running in this workshop. Let's try medium wave, frequency 1 megahertz. Okay, there's a few medium wave signals. If I go down in frequency, there's a big one there. That's 693 kilohertz. That's radio 5. That transmitter is only about 30 miles from here. It's a fairly high powered one. And there's a load more on the medium wave. What's that one on? 1055. That's Talk Sport, I think it's called. One 1.11415. Not sure what that is. Let's try up in the HF part of the spectrum. I'll put in 3 megahertz. No, I'll put 3 gigahertz in then. 3. Okay, there's a load of stuff down here. I don't know how much of that is real signal. We are on 3 megahertz center frequency. Or a lot of that could be a noise from switch mode power supplies I've got running. Let's extend the span a bit. That's a 1 megahertz span. Yeah, 5 megahertz. You can see the medium wave signals down the bottom. There's a big one out to the right. All that noise is almost certainly switch mode power supply noise from stuff I've got in the workshop. Yeah, there's a big one, but I know what that is. That's 10 megahertz. That's my GPSDO. So it's just radiating from the various cables I've got connected to it, and probably from its power supply cable. And go up a bit higher. There's the harmonic of it on 20 megahertz. Go a bit higher. 30 megahertz, another harmonic, and just basically a load of noise. Any HF signals are going to be pretty far down in strength and probably below the noise level in this workshop. So I think that just about concludes that demonstration. I think I'll now go up the garden and show you the other loop, which I use here all the time. So here we are up the garden, and here's the 1.2 meter diameter loop. And as you can see, because it's quite a big loop and it gets battered by the wind, I've got a support tube going up through the middle, which is plastic PVC pipe. This one is aluminium again. I think it's 3/8 aluminium. I originally had this with a copper, used copper tube, but copper's just too heavy and too soft, and it would just sag and get out of shape. So I eventually found some aluminium, which I think is 3/8 diameter, and I think it's used for central heating pipe normally. I'll take you in closer to have a look. There's the box with the amplifier inside, and RG58, which is about 100 foot of that, goes back to the house. And if I turn around, I can show you how far away we are from the houses. The nearest house is mine, just there, which is about 100 foot away. That's the whole point of it, getting as far away from houses as possible. And I did turn it around to minimize the noise. I think the main noise source is these power cables, which you may be able to see, that go across my garden. And you could definitely hear a difference by turning it round with the noise level going up and down. Other thing I did was I connected the outer of the coax down to earth through this cable and into the ground. It seemed to reduce the noise slightly. So that's about the end of the video. I hope you enjoyed it, and give me a thumbs up if you did. Bye.